There's a walkthrough of the 2013 paper 1. Check your answers as we go through the paper. So on to question 1. Well, one non-metal. Well, in the periodic table there's this zigzag line which separates the metals over on the left hand side from the non-metals on the right. So we're looking for everything over on this side, and then the other thing you need to note is that it has to be a solid. Well, you could have phosphorus, it's a solid, and notice it says name, so I'm putting in phosphorus rather than the symbol P. You could have sulfur, and the other one is iodine. Okay, this time we want to write a symbol, which is a liquid. Well, there are two liquids in the periodic table, so you should memorize these. They are bromine and mercury. Mercury is Hg. It's not in the table that's presented to us, so it can't be that one, but there is Br, which is there, so it's going to be Br. One diatomic element. Well, diatomic means two atoms that are covalently bonded together. It's not the noble gases, these ones. They're monatomic. They don't react with anything because they've got a full outer shell of electrons. But the other gases are diatomic. So hydrogen, nitrogen, oxygen, and all of the group 7 elements are diatomic. So you write the name of any one of those. For example, hydrogen and nitrogen, oxygen, etc. Okay, part 4, colourless gas. We get gas as non-metal, so we're looking for something over on the right hand side of the periodic table. And you could have nitrogen, oxygen, or any of those noble gases. Again, it's asked you for the name, so make sure you write something like nitrogen or oxygen, etc. Lastly, part 5, one transition metal. Well, the transition metals are in this part of the periodic table. So we've got Fe and Cu. And it's asked for the name. Fe is iron and Cu is copper. So either one of those will get you the mark. The most reactive element in group 1. Well, this is a group 1. Metals get more reactive as you go down the group. So in this case it's going to be rubidium. Again, I'm writing the name because that's what it's asked for. And the reason rubidium is the most reactive metal in group 1 is because its outer electron is further from the nucleus, so it's not attracted as strongly to the nucleus as the other metals in the group. The element of the electronic configuration 288, well, that adds up to 18. That's going to be the same as the atomic number, the number of protons, which is argon. It has an atomic number of 18. One element which sublimes, that's going to be iodine. You need to know that iodine and carbon dioxide sublime. Of course, carbon dioxide isn't an element, so it has to be iodine. On to part B. The name given to group 7 of the periodic table is the halogens. Chlorine is a green gas, or as you could say, yellow-green gas would be fine as well. Why must chlorine be used in a fume cupboard? Because it's toxic or poisonous, not harmful. Harmful isn't strong enough. Okay, so say it must be toxic. Then a balanced symbol equation for chlorine. Well, chlorine, when it's on its own, is diatomic. Remember, I said group 7 elements are diatomic. So it's going to be Cl2. Potassium iodide is Ki. Chlorine is more reactive than iodine, so it will displace the iodine from potassium iodide and take its place. So you get potassium chloride, and then iodine is produced. Because it's on its own, it will be I2. So that's 2 marks. And if you've got your 2 marks, you can get a third mark by putting a 2 in front of the Ki and in front of the KCl. Part 2. If you bubble chlorine gas into potassium iodide, well, potassium iodide is colourless. And we know that because potassium is a group 1 metal. And when a group 1 metal compound dissolves in water, just like a group 2 metal compound dissolving in water, it forms a colourless solution. So it's going to be colourless. 2, we'll think of what's formed in part 1. Iodine is produced. It doesn't dissolve that well in water, so when it's in solution, it's brown. This should be straightforward. The bottom number is atomic number, and the top number is mass number. The atomic number is 1, mass number 1. The protons is the same as the atomic number, so it's going to be 1. The number of neutrons, you subtract the atomic number from the mass number, so in this case it's going to be 0. Electrons 1. In an atom, the electrons will equal the protons. For oxygen, atomic number is 8. It's going to be 16 for the mass number. Protons 8. Neutrons will be 8. It'll be 16 minus 8. And then the electrons will be the same as the protons. Okay, water. Well, water is this. We'll just draw the stick diagram to start with. It's got 2 covalent bonds. So I'm going to draw the oxygen first of all, and then put in the 2 hydrogens. These lines represent a covalent bond, which is the sharing of a pair of electrons. Now, oxygen has 6 electrons in its outer shell. I'm not showing the inner shell. The inner shell would have 2 electrons. But the question is just asked me for the outer shell. So I'm going to leave those out. So I've got 2 in the inner shell. I already used 2 here, the axis. So that means I need another 4 electrons, which is there. Now, it doesn't matter if you've drawn it straight across, like that, for example. That is fine. There's your oxygen, your 2 hydrogens. You don't have to draw the shells. So you could have something like this, if you wanted to. Alright, so any one of those is correct. Calcium ion, its atomic number is 20. So when it is an atom, it would have 20 electrons. But because it's an ion, 2 plus, that means that it has lost 2 electrons, which will leave it with 18 electrons. I'm going to draw, here's my nucleus, first shell, second shell, and third shell. First shell will hold 2 electrons, then there will be 8 and 8 in the third shell. And you can see why it's 2 plus, because there are going to be 20 protons in the nucleus. That's what makes it calcium. Calcium will always have 20 protons. So it's got 20 pluses and 18 negatives, which is why it's 2 plus overall. So that's one of the subatomic particles. You are asked to state the number of subatomic particles. So I've said 20. You could draw a line from the nucleus out. So for example, you could do that as well, because you're asked to show the position of the subatomic particles. So if we go back, and I'll just write it beside the nucleus, there will be 20 neutrons. Subtract the atomic number from the mass number. So you've got a definition of alloy. So it's not just a mixture of metals. That might get you 1 mark. There's a mixture of different elements, and at least one of the elements is a metal. Allotropes, we've got different allotropes of carbon. For example, graphite, diamond is an allotrope of carbon. And the definition for it is, so there you can see it. And just to remind you, diamond is like this, a giant tetrahedral structure. All of these are carbon atoms with the covalent bonds in between. And then graphite which contains 6 carbon atoms forming a hexagonal ring. Like so, and then there are layers of those which can slide over each other. So both of these structures are made from carbon atoms, and they're in the same state. That means they're both solids. Alright, this type of a question is actually easier than it looks. Break it up into the different points. So we're going to explain the 3 physical properties. So take each one, do the melting point, the hardness or the softness of it, and then the conductivity. So we'll start off with the melting point. So you can either put it under headings, that doesn't matter. I'm just going to put in here for clarity, but I say you don't actually have to do or include these headings. So it's got a high melting point because the bonds between the atoms are strong. They require a lot of energy to break. So you could get a mark for saying that. If you've mentioned that the bonds are covalent, you would get a mark for that, or a tick for it, and that those bonds need a lot of energy to break. So I've got 3 ticks so far. We can then move on to the softness. So again, I'll just put in a heading. Remember, graphite is made up of layers, and those layers can slide over each other very easily because there are weak forces of attraction between the layers. So another couple of ticks for that one. And then the last thing we have to answer is the conductivity. Well, conductivity is either due to electrons or ions that can move, and in graphite it has to do with the electrons. So the reason it conducts is because it has free moving electrons, or you could say delocalized electrons. There's another tick. Oops. This is an indicative content question, so the ticks don't necessarily equal the marks that are obtained. If you've got 6 or 7 ticks, that'll equal 6 marks. 3 to 5, you'll get 4 marks. And if you've got at least 2 ticks, then you'll get 2 marks, unless things like your spelling and your grammar is really bad. Now, metallic bonding, let's just do a quick recap on what it is. You've got your positive metal ions. So these are not protons, which is a fairly common mistake. So these are the cations, the positive metal ions, and you'd always label diagrams if you're asked to draw them. And then they're surrounded by delocalized electrons. So just write those in. So that's what a metallic bond looks like. So you've got this regular arrangement of ions, and that is known as a lattice structure. There is an attraction between these positive ions and the delocalized electrons, and that's what holds the metal structure together. So if you're doing this definition, you could say that it's the attraction between the positive ions and the delocalized electrons. And I think it would be good to finish it off by saying, in a lattice structure, remember, lattice here just means a regular repeating pattern or a regular structure of something. In this case, it's a regular structure of ions, but a lattice can also mean a regular structure of atoms. So I would say 3 things for this. I know there are only 2 marks here, but sometimes it may be 3. Instead of saying lattice structure, you could reword it and say something like it's the attraction between a regular arrangement of positive ions and delocalized electrons. Okay, on to part 2. Malleable just means that it can be hammered into shape. So here we've got part of a metallic bond with the layers of ions. So if you were to hit it here, then this layer would move across the layer that's under it. But there's still an attraction between those positive ions and the delocalized electrons. So the structure still holds together. It doesn't go apart. So that's why they're malleable and indeed ductile. These layers can slide over each other without disrupting the structure. Question 3. Here you've got one substance, calcium carbonate, being broken down into 2 or more using heat. So that's a thermal decomposition reaction. 2, a reacting mass question. Now this one's fairly straightforward. Calcium carbonate has an RFM of 100 and calcium oxide is 56. So say this one is actually straightforward. You could just multiply this up to 600. You're multiplying by 6, therefore you would multiply this by 6. And I think it's good practice to be able to use moles, so I'm going to do that. So if we do this again, we've got our 100 as an RFM. We work out that we've got 600 grams, so 600 over the 100 will give us 6 moles. You can see that it's a 1-to-1 ratio, so you'd also have 6 moles of calcium oxide produced. Well, 1 mole of calcium oxide has an RFM of 56, so if you have 6 moles, then the mass would be 56 times 6. There's your answer. For part B, we're heating a sample of titanium to form titanium oxide. So the question here is, why is it necessary to lift the lid? Well, if you think about this, you're trying to react the titanium with oxygen. Now there's only going to be a small amount of oxygen in that crucible, and you want all of the titanium to react, so you have to lift the lid to allow oxygen in, and that's the answer. Now we have to work out the empirical formula, and the formula is basically how many moles of each element is present. So if we take a look at this one, we've got titanium, oxygen, and what we're trying to do is work out how many moles of titanium there are and how many moles of oxygen there are per titanium oxide. So we're using this data. We need to work out the mass of the titanium and oxygen. So mass of the titanium, well, I'm going to subtract the 18.34 from 19.36, and that will leave me with the mass of titanium. So 19.36 and subtract 18.34, that gives 1.02 grams, so I'll just put that in there. Then I'll work out the mass of oxygen. Well, this is the crucible plus the titanium plus the oxygen, and this one is the crucible plus the titanium. So the difference here is due to the oxygen. So we can work out the mass of oxygen by doing this calculation, and that gives an answer of 0.68. We can then work out the number of moles. To do that, we need to know the RFM. Titanium is 48, oxygen is 16. Now you don't use 32 for this because we want to know how many atoms of oxygen are present in titanium oxide. So it's always just the mass, or the relative formula mass of the single atom. And then we work out the moles, and for titanium that works out to be 0.02125, and for oxygen it's 0.0425. Obviously we can't leave it like this, so we need whole numbers. So we divide by the smallest, which in this case is the 0.02125, and that will turn this into 1, and then it will go into this one 2 times. So there's a ratio. That means our formula is TiO2. Okay, on to question 4. I've already plotted the results, and then we can draw a line of best fit. There, as you can see that it looks like a curve, so we're going to draw a curve. So part 2 then, exothermic just means that heat is given out. So during the reaction, you'll notice the temperature increasing, and that's what you can see from the graph. So there's a temperature increase. If you react an acid with an alkali, that's a neutralization reaction. And then you just write a balanced symbol equation. Anyway, just sodium hydroxide, you should just know that. Likewise, you should know the formula for the acids. So HCl is hydrochloric. They react to form the salt, sodium chloride, and then water. So there's 1 mark for the left-hand side and 1 mark for the right-hand side. Okay, to make pure dry crystals, so we need a few details for this one to show how we can make potassium sulfate. Over on the right, now you may not have done it exactly like this, but this is one way. So we can use a pipette to start with, and that will measure out our quantity of whatever. So in this case, I'm going to put potassium hydroxide into the conical flask. So this will be 25 cubic centimeters. A pipette is more accurate than a measuring cylinder, so I'm recording it as 25.0. I'll put the answers in a moment, but I'm just going to take you through the method first of all. So I've measured the volume of alkali into the conical flask. What I would then do is add some phenolphthalein. Of course, that will change it to pink because there's alkali in it. We then run the sulfuric acid from the burette into the alkaline solution until it goes from pink to colourless. So here we've got now our solution of potassium sulfate, but it contains indicator, and we've been asked to prepare pure crystals, so we need to get the indicator out of it. Now there are 2 ways you can do it. You can either look at the reading on the burette and repeat the experiment without the indicator, or what you can do is add some charcoal, and the charcoal removes the indicator. So you can see here the setup. Here we've got a flask with the charcoal in it. You would warm it gently for about 5 to 10 minutes. The indicator will be removed, and then you'd have to filter the mixture to remove the charcoal. And then the last couple of things you have to do, once you filter this, you then would have to evaporate half of the solution. So you're going to evaporate half, because if you evaporate it all, you won't get crystals. You'll just get potassium sulfate, and the water of crystallization will be driven out of the crystals. So that's why we evaporate half and then allow it to cool, crystallize slowly. So hopefully you can see that. We've got down to this stage here, and then you could also say that you dry between pieces of filter paper. Now, I would say pieces, not just filter paper, or not a piece of filter paper, not a paper towel. So just put that in. And if you're going to use an oven, it has to be a low temperature, because again, if it was a high temperature oven, then it would drive out the water crystallization. And the question has specifically asked for crystals. There's the balanced symbol equation. 1 mark for the formula on the left, 1 mark for the formula on the right. And if you've got 2 marks, then you can get a 3rd mark by balancing it. So here are 2 ways of defining solubility. Basically, you have 100 grams of water, and it's how much the mass of solid or the mass of solute that will dissolve in that 100 grams of water at a particular temperature. So why was the mixture filtered? Well, again, if you read through the question, you had 25 grams of the water, and potassium nitrate solid was added to it until no more will dissolve. So the reason why it's filtered is to remove the solid, or to remove the solid that didn't dissolve. And then heating the filtrate, you're told it's in an evaporating basin, and it's heated using a Bunsen. So we're going to use an evaporating basin here on a wire gauze, so we'll just use dashed lines. On a tripod, we don't need to draw a Bunsen burner, we can just write heat and put an arrow. And diagrams always must be labelled. So we put an evaporating basin or a dish with our wire gauze, and tripod. For this question, imagine you have a beaker with 100 grams of water inside, and it's at 40 degrees Celsius. Well, from the table, we're told that if 100 grams of water is at 40 degrees Celsius, it can hold 62.5 grams of potassium nitrate. That's the maximum amount that it can dissolve. If you had 62.6 grams of potassium nitrate, then 0.1 gram would not dissolve. So there we've said the 62.5 grams can dissolve. The solution becomes saturated. It's the maximum mass that can dissolve in 100 grams of water at that temperature. So if we have 72 grams that were added initially, and only 62.5 grams will dissolve, that means that 9.5 grams will remain undissolved. So on to part 2. Now remember, solubility is always about the mass of a solid or solute that will dissolve in 100 grams of water. So that's what you've got to work out, first of all. So in this question, it's asking you about 500 grams. Well, the table up here is for 100 grams. So you've got to work it out, first of all, for the 100 grams, and then scale it to 500 grams. So let's have a look. We're told that it goes from 60 to 40 degrees Celsius. So if you imagine that you have your beaker 100 grams. So we've got 100 grams of water. It's at 60 degrees Celsius, and at 60 degrees Celsius it can dissolve 108 grams of potassium nitrate. If that cools, so I haven't touched this water, so it's still 100 grams of water, but now it's at 40 degrees C. Well, how much can stay dissolved? Well, we're told, or we can see from the table, that it's 62.5 grams. So if you've started off with 108 grams being dissolved, and now at 40 degrees C, only 62.5 grams can stay dissolved, that means that there will be solid deposited because the excess can't stay dissolved. So the mass of potassium nitrate that will appear will be 108 minus the 62.5, and that will equal 45.5 grams. So this is the mass that will not dissolve in 100 grams. From the question, we want to know, well, if we had 500 grams and it was cooled from 60 degrees C to 40 degrees C, what mass would remain undissolved? Well, to go from 100 to 500, we're just multiplying it by 5. Therefore, we would multiply this by 5. And that will give an answer of 227.5 grams. Hydrochloric acid is HCl, and when hydrogen chloride dissolves in water, it forms hydrochloric acid. And what happens is that it dissociates or ionizes into the ions. So you've got H plus ions and chloride ions. Okay, strong acid. Well, strong acids are acids that completely ionize in water. So how could we distinguish between the three strong acids? So what about using pH paper or even universal indicator solution? Well, you cannot use these to distinguish between the three strong acids, and the reason for that is because all of them will turn the pH paper or the universal indicator red. They're all strong, so they will all have a pH of about 1. So we have to use something else, and we would use a pH meter. And just very simply, the one with the lowest pH is the strongest, because a pH meter can record if it's 1.1 or 1.2, etc. So pH paper universal indicator solution could certainly distinguish between different types of strong or weak acid, but not if they're all the same type of acid. You have to use a pH meter, and the same would apply to alkalis. Now in this question, we're using silver nitrate solution, and the solution is important. You need to include that, or you could say aqueous silver nitrate. When you see that, you should automatically be thinking in your head, this is testing for a halide. So testing for a halide, so that means chloride, bromide, or iodide. So if we add our silver nitrate solution to hydrochloric, well, hydrochloric is HCl. It contains our chloride. So we will get a white precipitate for that, or white solid. A precipitate is when a solid forms in a liquid. Hydrobromic, which is HBr, so contains bromide ions when in solution, and that will form a cream precipitate or solid when silver nitrate solution is added. And lastly, hydrogen iodide. Just remove that. Hydrogen iodide contains the iodide ions, and they will react with a silver nitrate solution to form a yellow precipitate. Okay, on to the ionic equation question. Now, ionic equation shows us the ions that actually take part in the reaction. So you can have spectator ions and they don't do anything. So when the silver nitrate solution reacts with hydrochloric, it forms our silver chloride, and that is the solid. So what we can do is, well, what ions will react to form this? Well, you can see it's made up of silver ions, and silver ions are Ag+. You'll find that on the back of your data leaflet. And chloride ions are Cl-, and that's balanced. Ionic equations have to balance, just like a typical balanced symbol equation. So the silver ions, they are part of the silver nitrate solution, which is why they'd be aqueous. The chloride ions is from the hydrochloric acid. They're dissolved in solution, which is why they're aqueous. But when those two ions come together, they form this solid. So that's our ionic equation. Now, you don't have to put in state symbols because it doesn't tell you to do that. So just leave them out. Only put state symbols in if asked to do so. Last couple of questions. Right, metal ion. Well, the test for metal ions, you can either have or do a flame test, or you could react it with sodium hydroxide solution. And a similar thing to that would be to use aqueous ammonia. Now, sodium ions don't produce any results with sodium hydroxide or ammonia solution. Therefore, we have to use a flame test. Now, there are only 2 marks, so it's not looking for a lot of detail here. So you could just simply write flame test. Remember, I'll just put this in. For a flame test, you would use nichrome wire, which would be dipped in concentrated hydrochloric acid. It would then be placed into the sample and then placed into the edge of a blue flame of a Bunsen burner. Okay, so if you're asked to describe it in detail, that's what you'd write down. But as I said, there are only 2 marks, so we can just say carry out a flame test, and sodium ions will produce a yellow colour, yellow or orange colour. Now, before I do this question, which just need to point out that this was taken from an older paper and an older spec. And the test then for metal ions were the flame test and sodium hydroxide solution. The ammonia solution didn't come into it. So what I'm going to do is I'm going to answer it using sodium hydroxide solution first of all, and then I'll give you the answer which you could now write using ammonia solution. So that's what we would do, and if you added sodium hydroxide solution to a solution of zinc ions, you get your white precipitate, which will dissolve when excess sodium hydroxide is added. Now the reason it's asking for the validity of the test is because aluminium ions produce the same result, and so the test isn't valid, because it doesn't tell you if it's zinc ions or aluminium ions. Okay, so that sort of gives you the context of the question when it was originally set. You now use ammonia solution. So what you could say is add ammonia, or you can write NH3 aqueous. You'll get a white precipitate. Now just point out that magnesium ions and aluminium ions will also produce a white precipitate. So at the moment, the ammonia solution doesn't distinguish between these ions. However, if we add excess ammonia solution, the precipitate dissolves. If magnesium or aluminium ions were present, the precipitate would not dissolve. So when you use ammonia, the test is valid.